This is our 2-3 lesson on linear functions, and we are starting off about talking about a constant rate of change. So we have a linear function due to having a constant rate of change, and we're going to talk about this chart, and we want to focus on the change in distance over the change in time. So that's really the change in y divided by the change in x. So when we are looking at this, if we go, remember this is your x, the time, and the distance is your y value, we would look and see that there is a change of 1. We're adding 1 every time, and in the y values we are decreasing by 25 each time. So it's not just that there's a constant change, it's the constant ratio. So if you look, the constant ratio is negative 25 over 1. And then every time it's negative 25 over 1. And so that would be our rate of change. Now, we're going to go ahead and start talking about linear functions. So a linear function can be written in the form of f of x is equal to mx plus b. Now remember, f of x is the same as saying y equals mx plus b. All right, so next idea that we want to talk about is x is always going to be your independent variable, the y is your dependent variable, and m and b, make that a b, are constants. And we're going to talk about m and b a little bit later in this lesson. All right, the graphical linear function should be a straight line. And it's made up of all the points that satisfy y equals f of x. Remember, f of x is the same as y. So we plug x in and we'll get the y values out. So the first thing we want to do is recognize a linear function given a table of values. So looking at this table of values, we want to determine if it represents a linear function, but I'd like to take it one step further and I'd like to discuss what that constant rate of change is. So if you look, these are already done for us. The x is increasing by 2, the y is increasing by 3. And so we're looking for the rate of change, the change in f of x or y over the change in x. So it's always a constant rate of 3 divided by 2. So there's a constant rate of 3 divided by 2, so yes, it's linear. All right, in the next one we have a constant change in x, but we don't have a constant change in y. There's a pattern, it's increasing by 1 each time, but it's not a constant change. So if we look at the ratio, the change in y, just like slope, change in y over change in x, 1/3 is not equal to 2/3, which does not equal 3/3. So since I don't have a constant ratio right here, it is not linear. All right, so we have 2 problems to try, and I'm going to add a third one on. So go ahead, show the work, and then determine if these are linear. All right, so let's jump in and talk about this first one. We have an increase of 7. So this is how I'm going to show my work. In case I make a little mistake, I have some work to back up my answer to get me more credit. This is decreasing by 9. And so you want to double check your numbers. All of these decrease by 9. So this one is linear. And the constant rate is negative 9 over 7. So it's linear because I have a constant change in y over x. Okay, looking at the next one, it decreases by 2 each time. And then the y value decreases by 2 and then 4, and be really careful right here. A lot of people say 6, but you're going from 1 to 0 and then to negative 7. So it decreases by 8. So yes, there is a pattern here that the decrease doubles each time, but it's not a constant change. If I take negative 2 divided by negative 2, that is not equal to negative 4 divided by negative 2. So at that point, this is not linear. All right, so I've added one extra example here to prove a point. So if we take a look at the x values, it seems like there is a constant change of 2. That's what it starts at. Increase of 2, increase of 2, and then it jumps to an increase of 4. So at this point, I'll have people tell me this is not linear, because they say, well, it's not a constant change. It goes 2, 2, and then 4. I'm not just looking for a constant change in y, I'm looking for a constant change in the ratio. So let's look at what y does. The y increases by 5, it increases by 5, and this time it jumps and it increases by 10. But if we look at that ratio, 5 over 2 is equal to 5 over 2. Is that equal to this 10 over 4? Yes. So even though it doesn't look like a constant change in y over a constant change in x, the ratios are the same, so this would be also considered linear. So you want to have some proof there. The constant change here is 5/2. All right, so that's how we determine if we have something that's linear, by looking for a constant ratio. All right, so on to the back. We are going to talk about slope. So the slope of a linear function is the ratio of the change in y, I'm going to put a fraction here, divided by the change in x. So the change in y divided by the change in x, or rise over run. Now just to throw this out, our slope formula is y2 minus y1 over the x2 minus x1, and we'll use this in our next lesson. So when I say the change in y, you really are finding the difference in the y divided by the difference in the x, and that's what we did in the last one. We looked at what it increased by. Now I can graph a line getting any 2 points, and what I could do is I can start with a point and then use my slope to work off of that. So that's what we have here. We have a slope of 2/3, and we have an ordered pair of 1, 1, which is your x and y value. And I'm going to call this my anchor point. I always have to have a starting point. And since I don't know the y-intercept, I'm going to go ahead and use this point 1, 1. So let's plot that on the graph, x, y, 1, 1. And then I'm going to do my slope, which is 2 over 3, which is a rise of 2 and a run of 3. So it's a positive slope, so I go up 2 and I go right 3. So remember, your slope is rise over run. You have to get up before you can run. If I go to do it again, up 2 over 3, I'm off the graph. So maybe, 2 points is enough to make a line. But if I ran out of space, I want you to remember, I could do -2 over -3. And negative divided by negative is a positive. So if I would go from my anchor point and go down 2 and then left 3, I will also be on my line. Now, notice I had a positive slope and my line is going upward from left to right. All right, in the next example, we're graphing with the slope of -1/3, and I'm going to put the negative sign on the 1. So it's a negative number. I get to pick one thing to be negative. And I have that ordered pair of -2, 3, which is my x and y. So I'm going to start with my anchor point. So go to x, -2, y is 3, plot that point. And when I go to do my slope, I'm going to go down 1 and then +3. So it's a -1 over a +3. So the rise is really going to be a fall and then a run to the right. So down 1, +3. Now, if I wanted to flip it, I could go 1 over -3. I get one negative sign. It can be in the top or it can be the bottom. So I start here, I rise 1 and I run -3. And then I can sketch in my line. So I don't need all these points. It really takes 2 points to make a line. I want to drive that slope idea home. Okay, so given an ordered pair in the slope, I put my anchor and I do my rise over my run. Positive slope should go upward, negative slope should drop. All right, now we're going to change gears. We're going to do something that we're not as comfortable with, but we're going to be working with it more this year. So we're going to talk about your X and your Y intercepts. Something that we've known, but we don't use a lot. So the x-intercept is the x-coordinate where a point crosses the x-axis. So I'm going to be asking you what two facts you know about the x-intercept. One, it's on the x-axis, and two, when I look at the ordered pair, the y value is always 0. So if you take a look at this graph we have here, and I pick something on the x-axis like 0, 0, 2, 0, 5, 0, negative 4, 0, no matter where I go on this x-axis, the y value is always 0. So the x-intercept is an ordered pair in which y is always 0 and a is the x value. Now, the y-intercept has the same idea. Let me try that again here. I lost a letter. The y-intercept is the y-coordinate where it crosses the y-axis. So what do I know? I know it's on the y-axis, and I know the x value is always 0 and the y value is b. So we just use the a to represent x and the b to represent y. So we have two different ordered pairs. Same idea. Here's my y-axis. If I'm at this point, I'm at 0, 4. I'm at 0, 1, 0, negative 3. And so I always have that y value of 0. All right, so when we go to do this, this is called standard form. And just want to remind you of that ax plus by equals c. That is another way to write a linear equation. It's called standard form. In true standard form, b and c are integers, and a has to be a whole number. So I don't need this in standard form, but since we're using the intercepts, I can leave it in standard form and work from it. So there are two things I know here. One, there's two intercepts, x-intercept and the y-intercept. And here's what I know. The x-intercept is on the x-axis, and it's an ordered pair where y is 0. So I want to find x when y is 0. So if I know that fact, I'm going to take that 0 and plug it into my equation. So to find the x-intercept, I substitute the y value with a 0. And so if I'm doing that, that cancels out, and I get 2x equals 12. Divide by 2, I get x equals 6. So to get full credit, if you tell me the x-intercept is 6, you want full credit, you want to put it in as an ordered pair. So that's what I'm looking for. Your x-intercept is 6, 0. It's its own point, and it's right here on the graph. Now, the two facts that I know about the y-intercept. First of all, it's somewhere on this y-axis, and second, it always has an x value of 0. So if I know that fact, I take the 0 and I plug it in. So it's 2 times 0 minus 3y equals 12. That's going to cancel itself out, and I have negative 3y equals 12. Divide both sides, and I get y equals negative 4. So I'm showing more work than you might need to, but you want to show some work to show that you have found your x and y intercepts. And then we go ahead and we graph that at the point 0, negative 4. And then we sketch in our line because it only takes 2 points to connect them. Okay, this has a positive slope, and so if we solve this for y equals mx plus b, we would also find it to have a positive slope. So I don't know the slope, I do know the y-intercept, and I do know the x-intercept, and that created a line. So make sure you're using your x and y-intercepts, especially for accuracy if you need to see where they intersect. All right. Now we're going to change gears again, and we're going to go to the slope intercept form. This is what we're used to graphing. So slope intercept form. It is written as y equals, or f of x equals mx plus b. M is the slope, and slope is your rise over your run, change in y over change in x, and b is called the y-intercept. Now there's a couple facts we want to remember about the y-intercept. First of all, it is my starting point, and it's on the y-axis. So starting point, and it's on the y-axis. Okay, so if we look at our first example, that's in standard form, ax plus by equals c. If I was graphing using X and Y intercepts, I'd plug in the 0 and solve it. I'd plug in the 0 and solve it. But I want to solve using slope-intercept form, and then I want to graph it. So cross the line, change the sign. I'm going to subtract that 3x. Okay, so when I go to do this, it is 5 minus 3x. These aren't like terms. I cannot put them together. If you don't like it written like that, you can always write it in the form and move it around. But notice the negative sticks with the 3 and the 5 is a positive constant. So given this information, my slope is -3 or -3/1. My y-intercept is 5, which translates to a y-intercept of 0, 5. So this is my starting point right here. And then I'm going to go down 3, 1, 2, 3, and right 1. So again, I get a -3 and then a +1. Down 1, 2, 3, right 1, and then sketch in your line. Now, I had a negative slope, so my line is dropping, which makes sense there. Okay, looking at my next one, if you would take a minute and rewrite this, it should really be 3/2 times y equals x minus 3. That y should not be looking like it's in the denominator. Okay, when I go to do this, I could divide by 3/2, but a lot of times we make errors because we don't think about actually dividing by 3/2, and people say it's 3/2 x. So I don't want to divide by a fraction. I know it's multiplication, so we typically divide. Instead of dividing by a fraction, we would multiply by the reciprocal. So I would multiply by 2/3. And we want to start doing this now because we're going to need this later in the year. So this would be 6/6, or these cross cancel. That's why it's the reciprocal. And I get y equals, distribute this, and I get y equals 2/3 x minus 2. Again, these 3's would cancel. So whatever it takes you to get there, there is my slope-intercept form. My slope is 2/3, and my y-intercept is -2, which is truly an ordered pair of 0, -2. So your y-intercept is your starting point on the y-axis. Your slope is positive, rise 2, run 3, rise 2, run 3, and we would create this line. And notice again, I have a positive slope, so it's rising from left to right, where in my other problem I had a negative slope, so it's falling from left to right. All right, last two big ideas are vertical and horizontal lines. So let's talk about those. Again, falling would be decreasing, going up would be positive slope. Okay, this is going to seem really simple when it's right in front of you, but when these get mixed in, we want to make sure we understand them and get them right. So I have on here a vertical line is when x is equal to a. So we have a vertical line here at x equals a. So I'm going to estimate this to be x equals 1.5 if we are getting specific. Any vertical line will always be x equals. It does not follow the rule y equals mx plus b because the slope here is undefined, and that is a really big deal. So this is a vertical line and the slope's undefined because if I go from here to here, I rise 1 and I run 0. I can't divide by 0. So I don't use the term no slope, I use the slope as undefined. Now, if I have a horizontal line, the y value is at b. So in this case, it looks like it's about 3.5. And in this case, the slope is 0. And that makes sense because I could rewrite this as y equals 0x plus 3.5. And if you look at that, 0x would disappear and I would just get y equals 3.5. So this one, y equals, follows the rule. So whether I have a positive slope, a negative slope, or a 0 slope, I get y equals. But the minute I have a vertical line, my slope is undefined, it is now going to be x equals. X is always that value. So don't get these confused, okay? Here's our rules again. So it looks simple here, but these are the ones that people mix up, so be careful with this. So I have x equals -3, and that would be a vertical line. All right, and I know it's vertical, and I know the slope is undefined. And so when you go to look at your graph, where is x -3? Well, right here it's -3. And right here, x is -3. And right here and up here, x is always -3 anywhere if I go up and down. So this would be your vertical line. It cuts through the x-axis at -3. I have a y equals 1. That is a horizontal line. And my slope here is 0. With that in mind, I would want to find out where is y equal 1, and it's right here. And y is 1 anywhere I go horizontally. So that is why I have a horizontal line at y equals 1 with a slope of 0. All right, in this last example, we have an application problem. So we have a road that's rising 2,500 feet above sea level to 7,000 feet in a total of 10, and it's in miles. We have to be careful with that. Find the average slope of the road. So first, we want to talk about the slope. Slope is always rise over run. And so when I do this, I have, it's rising, it goes from 7,000 down to 2,500. So I'm going to start with 7,000 and take away that beginning number. So that is going to be the change in the y values. Then we have to talk about the run. And the run is 10 miles, but I can't use miles and feet. So I'm going to multiply that 10 miles by the 5,280 feet in every 1 mile. And that will cancel out. And so I would be dividing by 52,800 feet. Okay, so my slope is going to be a big number. I get 4,500 divided by 52,800. Now I can go ahead and reduce and knock that down, and I end up with a reduced slope of 45 over 528. All right, now when I go to do this, that is a really hard slope to graph. So I want to go back and I want to use the X and Y intercept idea. I'm starting at 2,500 feet above sea level, and that is the Y value that we start, or the Y value, and we started at an X value of 0. So let's talk about using that Y intercept and X intercept. So I have 0, 25,000. That is my starting value. And then the other point is we do a horizontal run of 52,800 when we hit the height of 7,000. So we start at 0 feet and we go to a height of 2,500 so we start here and then we go 52,800 feet in a horizontal distance to get up to a peak of 7,000. So when I go to make this graph, I need to label two things. So I want to label my horizontal distance, and that is measured in feet, and I want to label my vertical distance, how far we are rising. It is really important to make sure your labels are correct. And then when I go to graph this, I have some really big numbers here. So I started by counting by 5,000s here. So 5,000, this would be 10,000, 15, 20,000, 25, then we have 30,000, and we hit 40,000 here, 50,000. So I've got some big numbers there. Here I'm going to count by thousands. So we have 2,000. So here's 1,000, 2,000, 4,000. So it's really important that you show an even interval. There's 5, there's 6,000, 7, and we hit 8,000. Okay, so now that I have that, trying to find the y-intercept and graph using this slope would be really hard. So I'm going to go ahead and use my starting point at 0, 2,500, which is right about there. And then I'm going to go and sort of find this point. I'm going to be estimating 52,800. So I would be right here, about 52,000 up to 7,000. And that would give me a pretty good sketch of my graph if we continued that pattern. So it's not always easy to use your slope, especially when we have big numbers. So it was important that we knew that our starting horizontal distance was 0. We were at 2,500 feet high. And then we had a total horizontal distance that we traveled up this hill, 52,800 feet from those 10 miles. and that gave us a final elevation of 7,000.